Okay, then we'll go ahead and get started. So we ended up last time talking about laser manufacturing as an enabler for remanufacturing. Okay, so this is a natural segue into end-of-life topics, which we'll be covering today. And we're going to look, instead of at end-of-life decision-making from the producer standpoint, the original equipment manufacturer standpoint, we're going to start by looking at the question from the end-user perspective. Now, a few of you have seen this case study, the vast majority of you haven't, but the question we're going to look at is whether a refrigerator should be remanufactured, reused at the end of its life, or produced as new. Okay, so we'll go through that. We'll have an in-class exercise there, discuss the topic, and then move into something that we like to call optimal end-of-life decision-making. So when you think about end-of-life decision-making, maybe it's a refrigerator, maybe it's a coffee maker. So we're going to look at a coffee maker case study here. Under a specific situation, you may be able to figure out optimally from a profit standpoint, optimally from an energy recovery standpoint, what should I do with this coffee maker. In fact, in Ann Arbor, it's a pretty simple decision. If you're trying to maximize your profit, depending on the price of the recycled materials, you're either going to shred it or you're going to landfill it. Most times you're going to landfill it. That's just a cost perspective. Right? Now, from an energy perspective, clearly you disassemble the whole thing, sort it out, and recycle all the materials. But there's a question about a balance between the two. First of all, what if there was a directive like the Waste Electric and Electronic Equipment Directive that exists in Europe? Okay, well, what would that mean? Now we have to recycle at least 70% of the mass. So what's my strategy? And if you think about it, this isn't a trivial problem. The reason is, let's think about a coffee maker. Maybe it's got 35 parts or more. Okay, so what decisions would I have to make? I would need to, first of all, figure out, what components am I going after, and what am I going to do with those components at the end of life? So I could shred the whole thing, or I could disassemble maybe halfway. And for some of those parts, I'm going to landfill. For other of those parts, I'm going to maybe send to a shredder if I haven't disassembled them completely. So you think about like a transformer or something like that on the interior. So you have some subassembly there. Or you might actually fully disassemble and recycle. There are literally millions of options. And if you just took a computer for a simple product like a coffee maker and programmed, all the costs and benefits to recycling and disassembly strategies and what have you, and you just let a computer run at it, enumerate every possible strategy, you could have a computer running for about 20 years and still not have an answer. Right? So there is, in this case study, some need for methodology development, number one, and number two, understanding sensitivity analysis, because that computer runs for 20 years, and now you want to change the cost of labor, or you want to change the distances for transportation. Under a different scenario, we have a globalized economy, so we've got coffee makers, perhaps made in the USA that are going to Europe, or vice versa. What does that mean for the end-of-life optimal decision making? Because that's the second part of today's session, and if we have time, we'll also cover some of the cost factors in recycling. Okay? So we're going to actually start with an in-class exercise. Usually we do them in the middle of class. This time we're going to do it at the beginning of class. Now, a few of you have seen this before. So I want to challenge you to think about this in a way that might be different from what you've seen before. Okay? In this case, this was a real case. So, basically around 2002, a colleague of mine came to me and he was asking whether refrigerators should be reused at the end of their life. And so he said, I've got a couple of IOE students. They'd be willing to work on this question. They need some guidance. Would you mind working with them? And we started going on this, and it was really interesting in the end. So what we're going to do here is just make a very simple set of assumptions so we can move forward here. And we're asking the question, okay, let's say that, and just pretend it's 2002 right now, that we're looking at refrigerators that were sold 10 years ago. All right, so now they're coming in at the end of their life. They're usable, but the consumers don't want them anymore because they remodeled or what have you. They want the stainless steel look in front or whatever reason. It's a working refrigerator or set of refrigerators, but they're not wanted by their previous owners. Okay, so suppose you're a place like the Reuse Center in Ann Arbor, and somebody comes to you with a refrigerator. Okay, and you're wondering, okay, should I take this refrigerator and let somebody else pick it up or not? Is that environmentally the right thing to do? What does it mean from a cost perspective? So, and here are just some numbers, okay? And this is not a numbers in class exercise. What we want you to think about are the strategy. What kinds of questions do you have? What answers do you need to answer this question? So, let's just suppose in 1992, the refrigerators being sold were, had about 1,000 kilowatt hours per year of energy consumption. And then over that 10 years, they lost about 30% efficiency. So we had some reasons to make these assumptions. Now, you could either go to the Reuse Center and pick up this old refrigerator, maybe for a nominal fee, or you could buy a new refrigerator. And I'll show you this refrigerator in just a minute. Okay, this is a real refrigerator for which there was a nice environmental product declaration online. I'll show you what an environmental product declaration is. And the question is, okay, well, should you buy this refrigerator or, should you buy the reused refrigerator? Okay, so just a few details here. That's what it looks like. Here are a few people laughing. Okay, so some details. Looks a little small. It's fairly quiet. It's CFC free, so the refrigerants systems basically is on isobutane. The blowing agent's cyclopentane. Okay, so let's just soak that in. Just some of the materials. I don't think this is all that significant, but here's the steels, the bulk of the composition. You do have copper, you do have aluminum. Plastics about 20%. Glass about 4%, and then you've got some blowing agents, refrigerants, electronic components, together making about 1%. So these are the materials, okay, for the new refrigerator. Now, I haven't told you what's in the old refrigerator. You can imagine a lot of steel, okay. In terms of energy consumption here, 248 kilowatt hours per year, okay. Now, if I look at the refrigerators coming in, 1,000 kilowatt hours, lost about 30% of their efficiency, so somewhere up around, let's say, 7 times the energy consumption of the new refrigerator. Okay? Why don't you put your minds to work, talk to each other, and then I'll ask you for some questions. Okay, it looks like this one has evoked some passion and discussion among the class. So what are the important factors here? I'm not looking for an answer just yet, but what kinds of questions do you have?
So we say.
Go ahead, Jerry.
One comment I just want to make, that just to add one more dimension to possibilities, is that I actually had a refrigerator that I wanted to get rid of. It was a chest refrigerator. I was contacted. I put it on Craigslist. I was contacted by a farmer who wanted to use that for outdoor grain storage. Yeah, outdoor grain storage for their animals or
Sell
something.
it at a fair price?
I gave it to him because it was a non-working, it was non-working. I would have had to replace it. So extending the life cycle by using these as shells.
Okay, in this case, we've got working refrigerators.
Okay. Wonderful.
I didn't mention that explicitly.
Okay.
Go ahead.
The life of the old refrigerator, how many more years would it run?
How many more years? So let's suppose that this new refrigerator lasts 17 years, and that this old refrigerator is going to last, say, 7 more years. Okay, and after 7 years, you're going to go buy this one that's 7 years old, so you have equal time periods, 17 years. Old plus new, well, I shouldn't say new, it's reused after 7 years. 17. You have to make some kind of time function assumption. So that's the one in this problem that we chose to make, but clearly you can make many others. What else do you want to know? Go, Arthur.
Be upgrading in order to buy this used one?
Okay, so what's the old refrigerator? So it uses a lot of energy, you mentioned that. It does have CFCs in its compressor and in its foam. For insulation. CFCs leak naturally, especially old refrigerators, so let's give it some rate of CFC loss per year. That will continue as long as those CFCs are not recaptured in the reuse process, which they wouldn't be. So what do you think? What kind of refrigerator you have in mind? Just so you go to Reuse Ann Arbor, what do you think you might see there if you saw these there? Does it look like this?
No.
Okay, so what does it look like?
Bigger.
Say again?
Bigger.
It's bigger. What else?
It's a freezer.
Bigger shell.
Yeah, probably an ugly color. Early 90s going on there. What's missing from this fridge? Yeah, freezer. Where are you putting the ice cream? So, this would be a non-starter in my household. Forget it. Ice cream happens to be important. I'm not a big fan of the environmental footprint, but this would be a non-starter. So the functions aren't the same. Let's be clear. Size, freezer, missing. Okay. What else do you want to know? Well, go ahead, Ryan.
The use phase typically dominates.
Use phase typically dominates.
For energy usage. So if I guess the point where that use phase energy use offsets the manufacturing, material extraction, transportation of a new refrigerator. That's where the decision point.
All right, so this is basically a solution strategy, right? So let's assume this is energy-using product, which it is. The use phase dominates. So we're talking about production, calling materials into play, manufacturing them, and end of life for your new refrigerator, because you know that your new refrigerator uses less energy. So let's calculate some kind of a break point and make a decision from there. Does that seem logical to everyone? Good.
What's the environmental impact of producing one new refrigerator compared to like 1 kilowatt hour of energy produced? Like,
That's a great question. Let me skip ahead because I have an answer to that. Whoa, sorry. Here. So what we're looking at is the environmental product declaration for that Electrolux refrigerator. And this will take you a minute to absorb, so keep staring at it. But let's go through its dimensions first, its units, okay, over here on the left. So there's a certain material resource consumption in kilogram. And this is broken down by phase: production phase, use phase, end of life phase, and a total, just adding them all up. Energy resources as a total kilowatt hours. So over 17 years. That's broken down into renewable materials, renewable energy inputs. The emissions are greenhouse gases in kilograms CO2 equivalent. Don't ask me what global warming potential value they used for the number of years, because I don't know. And I don't think the Environmental Product Declaration said. And that can make a difference, right? Depending on, if it's CFCs, for instance, those are long-lived in the atmosphere, have a high global warming potential. Oh yeah, this doesn't have CFCs in it. Okay, so maybe most of it is CO2. But it's hard to know from just a scorecard like this. Okay. Kilogram CFC equivalent, I think that idea is fairly clear. I mean, there are many ozone-depleting gases, but we need a common unit. Just like we used kilogram CO2 equivalent, we can use kilogram CFC11 equivalent, or CFC12 if we want it. Okay. Acidifying gases. So this is expressed as moles of proton equivalent. So if you think about the acidification of water, and you've got acids, right? So acids split apart in water, and they release moles of proton, lower the pH. So how acidified is a vapor? Let's say it comes in contact with sulfuric acid versus nitric acid. Well, sulfuric acid, H2SO4, has got 2 moles of protons per mole of sulfuric acid. For nitric acid, there's only 1 mole of hydrogen. So we can talk in terms of moles of proton equivalents. Right? This, again, taking all of the acidification potential and putting it into a single unit. Everybody understand the emissions, how this is going? Okay. Ground level ozone gases. Photochemical ozone creation potential equivalent. Who can tell us what that means? It's not that easy. There is an equivalent. So this is an equivalence. It's equivalent to ethylene. So it's ethylene equivalent. So one of the things that we did this term is we did a sort of a high level assignment 1, where you kind of learned about the pollutants that way. What that gives up is whole lectures where we talk about this stuff. So if you're interested in learning more about smog and ozone ozone depletion, we've got archived video on that. It's just for your interest if you want to learn more about it. And acidification is covered in archive lectures 12 and 13. Okay, but when we talk about photochemical ozone creation potential, the question is how reactive are the emissions in the atmosphere? So you know that VOCs, usually from transportation fuels, often from industrial sources like vapor, let's say paint lines, solvents, they react with, VOCs react with NOx in the presence of sunlight to form ground level ozone. Now the question is how reactive. Not all VOCs are the same. So it gets into a whole chemistry lesson, but basically there are methods to come up, rough estimates really, with ethylene equivalents. Okay, so this is smog forming potential. A lot of uncertainty there. Okay, eutrophication we've talked about before. This is kilograms of oxygen depletion potential. This is going to come up again in assignment 6. We can look at recyclable resources, waste, hazardous in general. Okay, so we've got those values for production, use phase, end of life. So what strikes you when you look at this? This is for the Electrolux refrigerator. Go ahead, Arthur.
Quite high. What is that?
End of life, where are we here? Yeah, we would normally call it recovery of energy. Let me see. Well, you can incinerate. Just looking at this. I believe it's combined in both. So this is expressed as a unit of energy. There's two ways to get energy. One, you can burn the materials that are, say, plastics, or you can recycle and sort of offset energy consumption. I believe this is both, but I can't tell you right off the top of my head because I don't remember. Go ahead.
Production than the use phase?
Yeah, so we were going with the energy using product assumption. This is intense in the use phase, but we're not really seeing that. The production here, at least if we're talking about greenhouse gases, is in excess of the use phase. Now look at that number for a minute. 120 kilograms of carbon dioxide equivalent. Is that a big number or a small number? It's tiny. So can somebody give me like an order of magnitude, like what that would be in everyday life? Pounds. So, well, no, take that back. 8.8?
Or 27 pounds, I think.
So I like to go in terms of miles. So driven? Okay, so let's try it this way. So just because I'm a little slow today. So it's about 0.9 pounds of CO2 for the average car when you drive it a mile. So, okay, so how many pounds is 120 kilograms? 250. Yeah, 250, say? All right, so roughly this is driving 250 miles. So if you're going up north this weekend, you're going to exceed that. Now that's the, it's hunting season's opening, right? So this is more than that for the refrigerator. So this is sort of a minuscule amount of energy, to use a word. Now, let's take this a step farther, because I know a few of you are energy systems folks. If I take the kilograms of CO2 equivalent, and I assume all the energy in the use phase is electricity. Now, there might be some repair and maintenance and some things happening otherwise. But let's just assume that all of it's a use. What kind of emission factor does that look like? If we say that it's 120 kilograms of CO2 equivalent to produce, say, 4,000 kilowatt hours. Just talking about energy intensity now. Was that very intense or not so intense? I'll tell you, this is about, if I take this number, 120, and I divide it by 4,200, it's about 0.03, roughly. That's 0.03 kilograms CO2 equivalent per kilowatt hour. 0.03. So energy systems, folks, is that a big number or a small number? Yeah, it's tiny, right? So the average U.S. grid's like 0.6. So this, this product declaration was in Sweden. Now they have a different energy mix, right? But this begs you to go, and I've got the environmental product declaration in the notes here. But if you go through it, you can't really decipher why that number is so low. So one reason could be that this is actually 1,200. Maybe not. It might be they're making some assumptions about renewables that this refrigerator is being used for. So it's not particularly clear. Go ahead.
Is it the energy consumed or the energy produced at the grid? Because transmission efficiencies are like 50%. Correct?
Okay, but that's not going to get you a factor of 10. That might get you a factor of 2.
Right.
Now this should cover, this is a life cycle assessment, so it should cover the transmission. So that just makes it even harder to believe, right? So something to think about. I don't have an answer for you. The point is, when you get numbers like this, so environmental product declarations are great because these are the numbers that folks who understand the environment, the kinds of things you can use to make decisions. But at this high level of aggregation and then just a page description about what it is, sometimes you're left with bigger questions, and you need to dive in rather than just take it as gospel. What else do you see from this? Anything else strike you? Go ahead, Sid.
Resources.
Yeah.
The consumer use is like 110.
Here?
Yeah.
Yeah.
Why should we spend so much?
What are the material resource utilization? What is that in the use phase? What do you think that is? No, because it's that would be an end-of-life issue or a production issue, right? Water? I don't think that this isn't one with like this is a good point actually. It doesn't have one of these what do you call it? Fill up your glass with water faucet. It takes materials to produce energy, right? It takes water to produce energy. It takes material to produce energy. So if I'm using coal, there's material resources to mine the coal, for instance, right? So you got to think upstream. So that is due to consumer use. It's not considered production here. Okay. All right. So what kind of decision would you make with this information? What do you think? I mean, you haven't gone through the numbers. What is your gut telling you? Want to take it? Go ahead, Sarah.
I'll go with the old refrigerator until I figure out a better option.
You're gonna pick up the old one?
Yeah. Until I figure out a better option, something that's even more environmentally friendly than the two of them. Something that I know, have a clearer data about.
Okay, but these numbers are pretty low, so you're just skeptical of the numbers. Maybe too good to be true? I'm unsure. Okay. Patty, you got?
There's a pretty high renewable energy resource going on there, so I kind of think that might be the reason for some of those low greenhouse gas emissions during the consumer use phase.
Just flagging over here in the energy resources.
So if that were the case, then if the greenhouse gas emissions from the new refrigerator are really that low, then it seems like that could be a better option.
So you're looking at about 50% of the grid that they're assuming here being renewable. All right, coming from Michigan, that blows your mind. And they got a fair amount of nuclear going on too. So you can get down to that minuscule level of energy consumption that way. And then the question becomes, how do you feel about that? Okay. And are you using the fridge there or are you using it here? Right, our grid's about 70% coal, 30% nuclear. Right, roughly. What else? Go ahead.
Analysis makes sense in the real life because people who are going to buy a new refrigerator would buy it no matter what. Like if they want a new one, they buy it.
For you, it's not for them, right? So you're supposed to be the ones who are educating others, right? So what would you tell your friend to do? If your friend came to you and asked, I care about the environment. Here's this sheet, and I got some numbers. What should I do? Right. So that's what we're talking about here. Go ahead.
There's a few other things to consider too, being a shipboard maintenance guy. You can do a lot of things to an older refrigeration unit to make it a lot more friendly and safer for today's type of atmosphere and everything that's going on. So potentially you could do some things to the older one for relatively low cost to make it better.
Okay, so
and at least make it more efficient and bring it back to its original efficiency. If not, remove some of the hazardous stuff that's in it and replace it with newer stuff.
So you can definitely go that route. So if you're a do-it-yourselfer, there's a lot that you can do to minimize the escape of the CFCs, to improve the efficiency of the compressor. That's one way to go. Cost came up. Doug brought up cost. So here, if you do the math, so roughly what the Reuse Ann Arbor shop would have been asking for, and the delta in electricity cost in Michigan, just because you're using so much more electricity in this refrigerator, in the end, you about break even. All right, so this isn't the most expensive new refrigerator in the world. It doesn't even have a it doesn't even have a freezer, right? So you can go different ways, right? Depending on your view of materials and what you think you can do with the old refrigerator. Go ahead.
17 years, right?
Yeah.
So if you go with the old one, aren't you gonna have to buy it like the same one as the new one anyway?
Yeah. So we made that assumption. So about 7 years in, you'll just go ahead and pick up one of these that will last another 10 years, and you'll have equal time periods to make a decision on. So you can do that. And I'll actually post what the numbers look like if you do that. But I don't want to focus really on the numbers here. I want to give people some intuition about how to think about these things. Ben, go ahead.
Of the old refrigerators, that means that we can increase the time that refrigerator can last. If for example, we keep the old body of the steel, but maybe we can change a compressor or some stuff like that.
So that will back to the point. So this can be done. In fact, you can make it into a new, bring it up to today's standards very easily. The question is, would somebody going to reuse sand? This would be a question you'd ask your friend, right? So, okay, well, are you planning to fix this thing up or not? Right? Yeah, so it's certainly doable, absolutely. So that's a third way to go. Let me just give you some more visuals that might prompt a few additional thoughts, because you're hitting all the points I was hoping you would. But let me go back to this refrigerator we looked at in the LCA lecture back earlier this term. Okay, we looked at, this is in the same refrigerator. This is a low energy refrigerator from Leo Alting's book. Okay, now let's just look at the parts in here. This is what a refrigerator is, right? You've got the box and the foam and the evaporator and the condenser and the compressor, and you've got a light, and you've got a steel base here with parts, and steel frame that's usually powder coated, door frame, packaging, right? So you got all this stuff going on with the new one. Now that packaging, of course, you wouldn't have in the reuse case. This is the bill of materials we went through really quickly, right? So each one of these things, you can take them back to their production. Kind of a lot happening here. This is just the one component, the steel cabinet, its weight, its manufacturing operations, the extent to which those were considered. You could do that for the whole fridge. This is the key thing that I wanted to get you to pay a minute of attention to. And that is, here are some of the materials that go into the refrigerator. You've got the crude oil, you've got the natural gas, you've got the coal, the plastic, the chemicals, the metals. They're coming from all over the world, right? So oil's a mix. The natural gas, and for the European case, is coming from the North Sea. Coal, some of it's coming across the ocean. Plastics, generally, refined as base plastic, maybe somewhere in the middle of Europe, and then you've got specialty makers. In this case, with the Leo Alting's refrigerator, you had ABS, basically a terpolymer there, made in Italy, PVC, Lorraine, polyethylene, all sort of coming to a manufacturing spot in Denmark for that refrigerator. Now, why do you think I'm showing you this in the context of that environmental scorecard?
Of transporting materials from one place.
Well, presumably it did. Presumably it did. So I want you to burn this picture into your brain, then I'll just go back to this one. Okay, why did you think that I show you this before I show you this? Go ahead, Andrew.
How it would be done in the source of the material?
Presumably, and again, a 2-page environmental product declaration isn't going to give you that kind of detail. But if they did it right, they followed the ISO 14040 guidelines, so they should be looking at the real process and the real location and include the transportation. So that should be there. What else am I fishing for? Sarah?
Where exactly is the impact happening is something that, that is answered by the second slide. Because if I'm generating, if I'm making these plastics elsewhere, it's the emissions in, say, Italy that I'm looking at, and not sitting here in the United States. So that's also an important aspect.
So we can focus a lot on Denmark or Sweden where it's made. Where it's used, we've already talked about, but you know, there is a global supply chain that needs to be considered. So this is the point that I was fishing for. That, you know, you look at something like this environmental product declaration, and you assume that all the emissions happen at the same time. Number one. Well, they don't. The use phase emissions are happening over 17 years. When we talk about photochemical ozone creation potential, and this is really interesting, right? Because what if it was just spread out over the supply chain? That would have far less impact or significance than it would if it was all happening in Los Angeles, right? You don't know that from this environmental product declaration. There are other issues here too about acidifying gases, right? There are places in the world that are far more sensitive to that than others. But you don't have any information about that given a sheet like this. So for folks who are, you know, capable of understanding the issues that are underlying an environmental product declaration, I think this is a very useful tool. But just making decisions on the basis of this alone, maybe from a consumer standpoint, it's not so bad. But for folks who are doing design work and trying to say, okay, I've got option A and option B, and I've got numbers like this. You know, and let's say there's even a small difference between the two, right? You can justify one or the other on pretty much any basis, right? So this is a hard business. This is what I'm trying to convey to you, okay? There was I'm remembering back now, I might not have shared this with you, one of the midterm evaluations. And this was a really striking comment. So, well, you know, I came in all fired up about eco-design, and you know, by the time I was 4 weeks in, I realized that you know this is really just a muddle, right? And you know, it's basically squelched my interest in the area. Something like, I don't remember the exact comment, right? So you know, I mean, we can take this at face value and go on with our lives and feel good about ourselves, or we can recognize what it is and what it isn't, right? And our goal here is to try to get you to think beneath the surface, and to ask questions like that. And if you've got dedicated staff, it's usually the larger companies do, you can at least get some answers. Say, okay, well, you know, eutrophication, you know, that looks like a big number to me. So where's that actually occurring, right? And if they find that there's no lakes around and it's just their eutrophication compounds, but they never contact water, well, then you got less to worry about, right? So, you know, the state of LCA as it applies to design decision making it's nascent, it's early.